We've all seen the scene. A character presses a button, the world freezes, and they stroll through a paused reality, passing shattered glass midair. This scenario feels plausible because it aligns with Sir Isaac Newton's absolute view of physics. Newton believed that a universal clock governed the cosmos, a clock that ticks at the exact same constant rate for everyone, everywhere, regardless of how fast they move or where they are located. In this framework, pausing time simply means pausing the physical positions of matter, turning the universe into a static playground. That view was overturned in 1905, when Albert Einstein introduced the special theory of relativity. Einstein demonstrated that space and time are not independent forces. They are interwoven into a single four-dimensional fabric called spacetime. Because of this unified fabric, moving through space requires moving through time. Pressing a freeze time button would force a discontinuity in the spatial dimensions themselves. Halting the clock triggers a sequence of physical contradictions, challenging the very stability of our reality. To see how these contradictions play out, we look at the only absolute constant in the universe, the speed of light in a vacuum. Human vision requires light particles, or photons, to travel from a source, reflect off objects, and enter our retinas at approximately 300 million meters per second. The millisecond time stops, photons become motionless. Light is no longer traveling to your eyes. This creates a paradox. While the rest of the universe is frozen, your body is still experiencing normal time. If you try to see by walking forward into these static photons, your retinas must process the light while time is locally paused. Forcing your way through stationary light particles would trigger a violent Doppler effect, shifting the photon wavelengths into high-energy gamma rays and X-rays. The immediate result is total, inescapable blindness, paired with a lethal dose of radiation hitting your retinas. The danger then extends to the air. At room temperature, nitrogen and oxygen molecules zip around at roughly 500 meters per second. When time stops, this kinetic motion drops to exactly zero. The atmosphere ceases to behave like a gas and becomes a solid lattice of stationary molecules. With infinite viscosity, the air would hold you in place like a block of concrete. You would suffocate instantly. You cannot draw frozen oxygen molecules into your lungs, and even if you could, the gas exchange in your blood relies on diffusion, a process that requires time and molecular motion to occur. Paralyzed and unable to breathe, you are physically trapped inside a solid block of air. In 1927, British astronomer Arthur Eddington coined the arrow of time, tying time's forward flow to the increase of entropy and the dispersion of energy. Because temperature is a measure of average molecular kinetic energy, heat cannot exist without movement. The cessation of all atomic motion instantly plunges the environmental temperature around you to absolute zero. If you somehow found the energy to push through these stationary atoms, you would face a final energy paradox. Displacing atoms out of your way instantaneously would generate infinite friction. That friction would release a surge of heat so intense it would instantly vaporize you. This demonstrates that the universe requires time just to remain physically stable. This is the Lorentz factor, the mathematical proof behind time dilation in special relativity. The equation shows that as an object's velocity, v, approaches the speed of light, c, time dilates infinitely until it stops altogether. From the perspective of a photon traveling at light speed, time does not pass. For light itself, the universe is already perfectly frozen. Modern quantum research reveals that time behaves in even more complex ways. In 2016, scientists synthesized time crystals, structures that move without energy, repeating patterns in time rather than space. Researchers studying Planck time, the smallest unit of time, now theorize that time might be quantized. If the universe moves in discrete frames, it freezes and unfreezes trillions of times per second. These theories suggest time might not be a flowing river, but rather an emergent property of quantum entanglement, a 4D block where our consciousness moves through a static past, present, and future. Understanding these paradoxes is the goal of quantum gravity, a framework that attempts to unite the physics of the very large with the very small. Current physics suggests that a pocket of flowing time cannot interact with frozen time without breaking the conservation of energy and tearing reality apart. Time serves as the fundamental connection between space, light, and entropy. It is the engine of existence, the prerequisite for change, warmth, and life itself.